Alright, welcome back to our final stretch of this lecture here. So we built a two-layer model. First we built a one-layer model, and it came up with not an entirely terrible estimate of what the temperature of the Earth would be if those assumptions were true. Then, as is the nature of the scientific endeavor, we tried to build a more complicated model, and we came up with this idea of a two-layer model, and made some assumptions that turned out not to be so great. Alright? But maybe we can fix that. I mean, we kind of got a hint from what we did in the second part of this lecture here that the key thing that went wrong was making each layer completely opaque to long-wave radiation. You know, the blankets that we started off with a one-layer atmosphere that was like one big thick blanket. And then when we made a two-layer model, we put two identical, equally good absorbing radiation, equally good at absorbing long-wave radiation blankets up there, and we ended up with a planet that's too warm. No heat was getting away at all. Well, but there is such a thing as like the atmospheric window where long-wave radiation does get transmitted through each of these individual layers. For that matter, it gets through the entire atmosphere. A certain amount of long-wave radiation was transmitted through the atmospheric window, if you remember that slide from NASA. So this idea that every layer of the atmosphere in this two-layer model, it was just the lower atmosphere and the upper atmosphere, was completely opaque, was a terrible assumption. We can fix that, though. That can't be right. I mean, you can see how that we could have done this even worse. I mean, if I had started with a one-layer model and had said, now let's make a 1,000-layer model, well, we wouldn't have made each of the 1,000 layers completely opaque to long-wave radiation. We would have made each of them have some fraction of the long-wave radiation get through that layer. It was partially opaque. It was translucent, to use the right word. It got some of the long-wave radiation through layer 0, layer 1, layer 2, all the way up to layer 999. Okay, we can play that same sort of game. So let's not do a 1,000-layer model. Let's do a two-layer model. We're still going to make an atmosphere that has two simple layers, just because I don't want to do the math for a longer one. You're going to see there's a lot of math in this one. All right, but what we're going to do, well, let's talk about shortwave radiation first. Let's see. Originally we said that the atmosphere was completely transparent to shortwave radiation, except for what was reflected, of course. So 340 watts per square meter hit the top of the atmosphere, something, clouds or the ground or whatever, was reflecting 102 watts per square meter. We don't really care what it is because it's gone. But, we know that's not right. We know that some shortwave radiation gets absorbed by aerosols and so on along that way in each of these layers. So let's make a little assumption. I mean, if we're just trying to play a game here and figure out if we can make our model better, let's take that 238 watts per square meter that's not going to get reflected. This is going to be used to warm something up. Now, previously, none of it was warming up the atmosphere, it was warming up the ground. Let's play a different game this time. Let's say 10% of the radiation gets absorbed by each of the layers it passes through. So, now I'm going to make my life a little simpler here, and rather than put these numbers on here, like 238 watts per square meter, labeling all these arrows and all that gets complicated fast. So let's make a little notation thing to save some space here. Let's call this E. E is often a symbol in radiation that means like the flux of radiation. So E watts per square meter are going to come down from 96 million or 94 million or whatever it is miles of cold dead space and make it to the top of the atmosphere and not get reflected by something. This is radiation that's going to get absorbed by something. Probably the ground, but maybe ozone or something like that. Alright, so here's 238 watts per square meter that hit the top of the Earth's atmosphere. And we've said 90% of that's going to make it through. Okay? So 90% of that E, or 0.9 E, makes it through the upper atmosphere and encounters, is incident upon, to use the right jargon, the lower atmosphere. Okay? Now, 0.9 E, which we could do the math if we cared to at the moment, but we don't care to, of that shortwave radiation hits the top of the lower atmosphere, and 10% of that gets absorbed along the way, so 0.81 E of that shortwave radiation is going to make it through to the ground. That's 0.9 of 0.9 E. Okay? So 81% of E shortwave radiation will have made it through the atmosphere to the ground. In other words, about 19% will have been absorbed by the Earth's atmosphere. If you remember back to that slide from NASA, think the right number was about 25% of the Earth's the radiation from the sun gets absorbed by ozone and water vapor and aerosols in the atmosphere and so on. So this is actually not, I mean, this is a better approximation than saying none of it got through the atmosphere. I'm okay. So 81E made it to the ground. Meanwhile, the ground itself emits long-wave radiation. We don't yet know how many watts per square meter that is in this new, more realistic two-layer model. So let's just give it a name, and I don't know why I chose XG the time I made these slides. I made these slides a different semester, and I think the textbook we were using that semester used this notation of XG. I think it's X, what we're solving for, G from the ground. Okay, so a certain amount of long-wave radiation is being emitted by the ground. I'm going to call that XG. Ultimately, that's what I'm solving for, so then I can use Stephan-Boltzmann law and get the temperature. Alright, XG is emitted by the ground, and it hits the lower atmosphere. Now, previously we said all of that was absorbed, but now we know it's not going to be. Let's make a better assumption than saying all of it gets absorbed. This time, let's say 90% of it gets absorbed. That's less than 100% of it gets absorbed. Okay? We are at least taking a step towards a better model here. Okay, so if 90% of XG, the long-wave radiation being emitted by the ground, is getting absorbed by the lower atmosphere, then 0.1 XG gets transmitted through the lower atmosphere. Okay, like atmospheric window kind of thing. Okay, this is radiation, long-wave radiation that made it through the lower atmosphere and is now penetrating into the upper atmosphere. Okay, now let's keep the same assumption that the upper atmosphere has the same properties as the lower atmosphere. It also will absorb 0.9, 90% of the long-wave radiation that hits it. So a total of 0.01 XG of the radiation that was emitted by the surface of the Earth will make it out to the sun. 0.01 because it's 0.1 times 0.1 XG. Okay? 10% of the radiation emitted by the surface of the Earth. So in this case, 0.01 XG is the long-wave radiation that was emitted by the ground. It made it all the way out. It got transmitted all the way out into space and is gone. It was not absorbed by the lower atmosphere. It was not absorbed by the upper atmosphere. This is the atmospheric window. It's about 1% of the radiation that was emitted by the ground. You know, that slide from NASA, it was a bigger number than 1%. It was something like 19% or something like that. Okay, so we're not great yet. We still don't have quite, I mean, I would rather these, but let's not mess with the numbers right now. Let's just say, hey, okay, we can always play with this and say, oh, maybe each of these layers didn't absorb 90%, maybe they absorbed 85%, and then see if that works. Or we could play with these numbers until we got a more realistic fraction of the radiation emitted by the ground that was transmitted through the atmospheric window. We're just not there yet on slide 43. So when we switch to slide 44 there, we're going to start thinking about what the layers of the atmosphere are doing then. Well, each of them is going to be emitting long-wave radiation as well, which is those green arrows that I've added onto that diagram there. Now, I don't yet know how much radiation the lower atmosphere emits, so I'm going to use the symbol XB. B is for bottom, like bottom of the atmosphere or something. I'm just remembering from the handout or whatever we had a different, or the textbook or whatever we used a different semester. If XB of radiation is going up and XB is going down, okay, we got that. Now, the XB of radiation, that many watts per square meter of long-wave radiation that was emitted by greenhouse gases in the lower atmosphere that heads down to the surface of the Earth, no problem. Long-wave radiation, when it hits the surface of the Earth, it's absorbed. We don't need to worry about reflection or transmission or anything like that. The XB watts per square meter of long-wave radiation heading up from the lower atmosphere up into the upper atmosphere, well, some of that is going to get transmitted, right? We decided that each of these layers of the atmosphere transmitted about 10% of the long-wave radiation that hit it. They absorbed 90% of it. So of that green arrow, XB that was going up from the lower atmosphere, 10% of that, 0.1 xb, makes it through the upper atmosphere and up to space. This is long-wave radiation emitted by gases in the lower atmosphere that was actually transmitted through the upper atmosphere and goes into space. Okay? The upper atmosphere is also made of gases and matter and greenhouse gases, and they emit long-wave radiation too. I don't yet know how much. We're going to be able to figure it out. But we're going to call it XT. Again, X because that's what we're solving for. T for the top of the top layer or something. Again, just symbols from something I had before. So that layer of the atmosphere itself emits XT watts per square meter. Some up and some down. But of course, this radiation that goes up from the top of the atmosphere, that's just gone. But that XT, that red arrow downward, that is going to encounter the lower atmosphere. That is long-wave radiation from the upper atmosphere that's going into the lower atmosphere. And we've already said that each of these two layers absorbs 90% of the long-wave radiation that hits it, which means 10% of the long-wave radiation that hits it gets transmitted. So down at the ground, we observe that 0.1 xt watts per square meter of long-wave radiation that was emitted by the upper atmosphere makes it to the ground. Okay, we have now built a model that shows these streams of radiation going up and down. It looks horrible. This looks horrible. But you know what? This is actually a thing we can solve. This is a model that a math person knows what to do with. Because, once again, we're going to be making an assumption that there's energy balance here. At each level or layer or in this model here, we're going to be assuming that exactly the same amount of radiation is going down is going up. Okay? So in order to do that, for example, where I've circled there at the surface of the Earth, how much radiation is going up? Xg. That has to be equal to the amount of radiation going up. I'm sorry, going down. How much radiation is going down? Well, it's the sum of 0.81 E, the shortwave radiation that came all the way through the atmosphere down to the ground, XB, the long-wave radiation emitted by the lower atmosphere and making it to the ground, and 0.1 XT, that little fraction of the long-wave radiation emitted by the upper atmosphere that made it through the lower atmosphere down to the ground. That has to add up like that. Xg equals 0.81 E plus XB plus 0.1 XT. Okay? A mathematician would start seeing hope here. Because we could do the same thing for like the top of the atmosphere. We could say, okay, we have to have the same amount of radiation going up as going down. How much radiation is going up at the top of the atmosphere? Well, it's the sum of the black arrow and the green arrow and the red arrow. So it's the sum of 0.01 xg and 0.1 xb and xt. And that has to be equal to the amount of radiation going down, which was E. Okay. And for that matter, we could talk about like this place, another place in the atmosphere where again there needs to be thermal equilibrium. We need to have just as much radiation going up and going down. So like for example, at the boundary between what we're calling the lower atmosphere and the upper atmosphere, we have a certain amount of radiation going up. It's the black arrow and the green arrow. And we have a certain amount of radiation going down, the blue arrow and the red arrow. And we can transfer each of those numbers over there and make those things equal. Now, with a little bit of rearranging in algebra and so on, look what you have here. We've now found three equations that describe this radiation balance. One was associated with the ground, one was associated with the top of the atmosphere, and one was associated with that middle part of the atmosphere there. But they're three equations. And they look like a mess. They're not so bad. And keep in mind, E was just sort of a placeholder to save us space for that number. What was it? 278 watts per square meter. So wherever you see E, it's just a number. But this is something that you saw even in like high school algebra classes. This is called a system of three equations and three unknowns. In this case, the three unknowns are Xg, the amount of radiation being emitted by the ground, Xb, the amount of radiation being emitted by the lower atmosphere, and Xt, the amount of radiation being emitted by the top of the atmosphere. And in general, three equations and three unknowns in general can be solved. I mean, I don't know about your high school Algebra 2 class, but my high school algebra class was full of crap about solving different systems of equations. 2 equations and 2 unknowns, 3 equations and 3 unknowns, 4 equations and 4 unknowns. That's about as far as we got, because it gets complicated. But that was what a big chunk of like Algebra 2 was. Now, I'm not expecting you to remember how you did that, okay? That is not a valuable take-home lesson from an 500 level environmental science class. That you can solve such things can be done. You might remember there were techniques like substitution, there were techniques like the cornfield method, there was a matrix inversion method, I forget. There were several ways to solve, if I remember right, there were like 3 or 4 different techniques to solve a system of 3 equations and 3 unknowns. But if you actually apply one of those 3, I actually used substitution because I can't really remember how the other ones work that well. You can actually solve, and it takes a fair amount of algebra, but you can solve that xg has to be equal to, in this case, 582 watts per square meter. The amount of radiation being emitted by the ground, the only way this model works out is if the surface of the Earth is emitting exactly 582 watts per square meter, which, well, let's see, that's a lot lower than 712 watts per square meter, which you might remember was our horrible answer when we were saying that both of these, the upper atmosphere and the lower atmosphere, were both completely opaque to long-wave radiation. By letting some long-wave radiation get away, we came up with a lower number of the amount of radiation that was being emitted by the surface of the Earth. Effectively, we still have 2 blankets on the Earth, but they're not as warm of blankets as they were before. You can plug that number of 582 watts per square meter into Stephen Boltzmann's law, and you get a temperature of 318 Kelvin, which is 45 Celsius, which is 113 Fahrenheit, which is still too warm, but a major step in the right direction from 144 degrees Fahrenheit, which was our previous answer. Just by adding in this idea that each of these layers was not completely opaque to the long-wave radiation that was going through it, we've improved our model dramatically. Now, are we on the right track then? Well, it does seem like saying that these layers were not completely opaque, but they were letting some long-wave radiation through was a big step in the right direction. Looks like that was a bad assumption originally that we have now fixed. Okay, now we assumed that each of these layers, the atmosphere was letting 10% of the long-wave radiation get transmitted through, 90% get absorbed, and we came up with an unrealistically low amount of radiation getting through the atmospheric window and an unusually high temperature for the Earth. But this sounds like we're on the right path. With some experimentation, we should be able to come up with a value. Oh, maybe it's not 90% gets absorbed, maybe it's 85%, maybe it's 82%. With a little bit of, messing around on a piece of paper or with an Excel spreadsheet, it seems like you could probably play with numbers here and get this much closer to correct. So this idea before of just piling more and more layers onto the atmosphere without adjusting how transmissive they were to what their monochromatic transmissivity for long-wave radiation was a bad idea. We now have a better idea about how to do this. Let's think about that. I mean, let's actually try this. Let's see what happens if we actually make each layer of the atmosphere less good at absorbing the long-wave radiation. That is to say, give it a higher transmissivity to the long-wave radiation. If our model is working the way I think it does, and this is the point of a conceptual model, is to try this, if the model works the way I think it does, then by decreasing the amount of radiation, of long-wave radiation that each of those layers of the model absorbs, should make the planet cooler. We should have less of a greenhouse effect. Let's try that. So let's say, here's our previous model, our more realistic 2-layer model, where we had 90% of the long-wave radiation getting absorbed by each of those 2 layers. Let's change that to, how about 50%? Okay. That seems like a big change, but let's see what happens, okay? So notice if you actually take a close examination of this slide and the previous slide, 58, you can see that the numbers have changed all over the place here. Like, for example, if you just follow the black stream of arrows here, the surface of the Earth is still emitting some xg, watts per square meter of radiation. Now we're saying half of that radiation got absorbed by the lower atmosphere, but 0.5 xg got transmitted up into the upper atmosphere. And in that upper atmosphere, half of that got absorbed, but 0.5 times 0.5 xg, or 0.25 xg got transmitted and is now at the top of the Earth's atmosphere going out into space. And you could follow through what happened on the blue layer, I'm sorry, the green arrows that show what happened to radiation that was emitted by the lower atmosphere, or the red arrows that show what happened to radiation that was emitted by the upper atmosphere, and we could once again use that information to take thermal equilibrium and find three equations and three unknowns. One equation corresponds to the fluxes of radiation at the top of the atmosphere being in radiative balance. One is for the middle of the atmosphere, one is for the bottom. And again, you could use your high school algebra skills that we have all forgotten, and in this case it would be substitution would be a good way. And when I plug those numbers in now, I get a number of xg being 320 watts per square meter. Okay, that is certainly a lower amount of radiation being emitted by the surface of the Earth. My hypothesis that this would make the Earth cooler appears to be true. In fact, if you plug that number of 320 watts per square meter into Stefan-Boltzmann law, you get a temperature at the surface of the Earth of 274 Kelvin, which is the same thing as 1 degree Celsius, which is the same thing of about 33 degrees Fahrenheit. So yeah, my hypothesis was right. Changing this transmissivity of these layers for long-wave radiation, changing their monochromatic transmissivity, is controlling the temperature of the Earth. You can see the lesson of the greenhouse effect in here, right? I mean, we got a better answer. We're getting closer to the right answer here. It looks like the temperature of the Earth is being controlled in our little model here by how good the different layers of the greenhouse gases are in the different layers at absorbing long-wave radiation versus transmitting it. Do you see the environmental science lesson here, right? By adding greenhouse gases in the right bands so that they are increasing. Remember that business we had where in the previous lecture where we showed how, like, at this range of wavelengths, like the atmospheric window, it didn't matter how much greenhouse gases were. In these ranges of wavelengths, which I didn't have a name for, the greenhouse gases already absorb all of the long-wave radiation. The atmosphere already is opaque at those wavelengths. But at the right wavelengths, where the atmosphere was currently absorbing some long-wave radiation, that's where we had this interesting problem. That's what we're solving here. We're seeing how as we increase the amount of greenhouse gases in the atmosphere and made the atmosphere overall more opaque, that is to say, transmitting less of the long-wave radiation and absorbing more of it, we controlled the temperature. That's the environmental science lesson here, right? We're seeing, with even as simple of a tool as this stupid two-layer model that I made on a PowerPoint slide and solved using high school algebra skills, we figured out that the concentrations of these greenhouse gases and how they affect the transmissivity of these layers for long-wave radiation controls the temperature of the Earth. That is a big deal. Man, I wish I could teach this in the 100 level classes. They would totally dig seeing that even high school level math skills and so on can show that this has to be the case. Now, still, even with these new improvements and so on, my two-layer model is still only doing this so well. I mean, we're going to need better skills than this. Now, one part of the story is we could, of course, have more than two layers. In fact, a real atmospheric model, like the climate models that you're going to be learning about in the third module of the course that are telling us what's happening to climate and so on, they often will have dozens to hundreds of layers. Let's say it's some configurations of some models have like 100 layers. Each of which, of course, only absorbs a small fraction of the radiation passing through it, but there's 100 of these layers. But the result is you get a system of 100 equations and 100 unknowns, and if you think in high school algebra you learned how to do that, you most certainly did not. It takes supercomputers to solve those kinds of problems, but we're going to get there. Another thing is, I don't really like this just sort of pulling numbers as to what I think the transmissivity of each of these layers is, or how absorptive I think each of these layers is. What's their monochromatic absorption of long-wave radiation and the monochromatic transmission of long-wave radiation. So I don't really like that. I would rather have information. I would rather actually know what they are rather than just saying, let's try 90, let's try 50%, let's try 90%, let's try 50%. No, let's have a way of doing it. Okay? So we can either be thinking about this as having more and more layers, or we can be thinking about this in terms of actually having some meaningful understanding of what those layers are going to be in terms of what their absorption and transmission is going to be. Okay. If I want to actually divide the atmosphere up into some larger number of layers, whether that number is 2 or whether that number is 100, what I'm going to need to know is how thick each of those layers is, and I'm going to need to know how good that layer is at absorbing the kind of radiation I'm talking about, like long-wave radiation. And that's going to have to tell me things like, I'm going to need to know things like how many absorbing bodies, like carbon dioxide molecules, methane molecules, nitrous oxide molecules, there are in that volume, like per cubic meter or something like that. Okay, we're going to want to actually be able to figure out the transmission of long-wave radiation through these little layers that we're now making up, and the absorption of long-wave radiation through each of these little layers. How are we going to do that? We're going to need a good friend called Beer's Law. Okay, now Beer's Law actually has nothing whatsoever to do with the beverage. His name was Lambert Beer. Actually, no, I'm sorry, his name wasn't Lambert Beer. I'll get you this exact name. It's more strictly known as Lambert Beer's Law, but everybody calls it Beer's Law. That is for figuring out, if I have a layer of the atmosphere, how do you figure out how much radiation gets through that layer, how much radiation gets absorbed by that layer, and so on. It's a powerful tool for any kind of application in which radiation has to go through stuff. The right word for stuff is an attenuating medium. A path through stuff that can attenuate, that is to say, reduce the total amount of radiation that is passing through. I'm indoors right now, but my cell phone would still work because, by and large, the radio waves that are transmitted by the tower, cell phone tower, are generally transmitted through walls, but the wall does attenuate the signal somewhat. And if I'm in the basement where there are more walls between me and the tower, I have less signal. We're not worrying about signal here, okay? We're worrying about transmission of long-wave radiation, transmission of shortwave radiation, and so on. Lambert Beer's Law is going to be a great tool for that, but not till Lecture 2C. Let's go ahead and answer 2 quick questions about this. Excuse me, I have the hiccups. Before we finish up this lecture. Question 5. At any height in our N layer model, N being 1 to 100, I don't care, we need to have A, just as much radiation up as down, B, information about how high above the ground this level is, or C, information about the pressure of this level. Which of these is going to be helping us with our N layer model? Make a choice from those 3 options and get a little, click on the one below that is your choice and get a little feedback before we go on to our final question.